So please welcome Rich Geldreich, Dan Ginsburg, and Jason Mitchell from Valve.
Hi, good afternoon. My name is Jason Mitchell. I'm a software developer at Valve. And this afternoon, Dan Ginsburg, Rich Geldreich, and Peter Lohrmann and I are going to share with you some of our thoughts and latest developments in moving our technology to OpenGL. I'll be providing sort of some framing at the beginning and the end of the talk about sort of our high-level thinking and provide some data to you about what's driving our thinking around OpenGL. And Dan is going to dip into a lot of details about the general problem of what it takes to go and ship shaders on OpenGL, because that's a surprisingly unsolved problem at this point, I think, to do something super competitive in that area. And then Rich and Peter are going to show you a demo of some upcoming open source tools that we're working on for OpenGL debugging. So first of all, you know this, I think, already. But one way or another, you're going to ship OpenGL. That may be, hopefully not, an afterthought port to alternative platforms. Maybe one way you had thought of it in the past from your mainstream D3D Windows-centric thing. I think we're here to convince you that I think today that what we've, I think, ourselves become convinced of is that you can just ship OpenGL in general. Obviously, it's everywhere. It's the 3D API that you use on SteamOS. And also, of course, on Linux in general and other desktop platforms like Windows and the Mac. We're finding, interestingly, that in China, which is a market that we're focusing on a lot more recently with our recent launch of Dota in China, that China is overwhelmingly running Windows XP, which has some interesting implications that we'll get to. Obviously, in mobile, OpenGL is ubiquitous. Even big boy OpenGL is becoming available on the mobile platform with some of the new products that NVIDIA has announced. And WebGL is a way to get at 3D in a browser as well. The Steam hardware survey shapes our thinking, probably a lot of yours as well. One simple way to kind of break down the hardware that our users have is along the lines of, say, call it a DirectX 11 part, a DirectX 10, 10.1, or OpenGL 4.4. You can see, obviously, with the correspondence of, say, OpenGL 4.4 is basically like DirectX 11. You get pie charts that look basically the same. And this is what we see currently today amongst Steam users that run the hardware survey, which is predominantly, at the moment, a Western audience. Now, that's all hunky-dory and a fairly optimistic view of the world. If we take that pie chart on the left and also show it next to the OpenGL context that you will get today, this is acquired from the Steam hardware survey itself, the Steam client, you will get back sort of more of a mishmash of context available on Steam user systems. That's due to a variety of things. Hardware vendors maybe not yet shipping their OpenGL 4.4 implementations, or users having old driver installs. That sort of thing. Over time, we hope that the picture on the right starts to look more like the picture on the left, meaning people have up-to-date drivers. They have drivers that allow you to get to the most features that are actually available on their hardware. Some of the challenges in that area, vendors will have varying levels of XP support. You could certainly understand them for maybe forking that driver effort and maybe leaving that in more of a sustaining mode. Apple at this point is currently at 4.1, and we'll talk more about that a little later. If you look at operating systems across Steam users, you'll see, again, the fairly Western audience in this data. We have a large uptake of Windows 7, even Windows 8. There's that little blue wedge of Windows XP still laying around, and so on. Even with that little wedge of blue XP there, that has implications for your total available market if you're shipping DirectX. Independent of whether you're shipping across platforms, if you choose to ship on DirectX, say 10 or 11 on Windows, you will be limiting your total available market in this way, in the sense that the systems, in theory, the hardware could, two-thirds of those folks could support, say, OpenGL 4.4 or DirectX 11 class functionality. But because of the dependence of DirectX 10 and 11 on Vista and up, your total available market goes down. Likewise, by a different percentage for DX10 products if you rely on those features. In OpenGL, that's not a thing. those total available markets numbers don't change. Of course, this is assuming, again, that those users are getting the latest drivers, that the hardware vendors are making them available. So this is kind of the rosiest possible picture there, but this is kind of how we think about this. As I've been alluding to, emerging markets are becoming increasingly important to us. The most important example for us right now is Dota, which we've been shipping in China. And we're finding that Windows XP is extremely prevalent there. One thing that I should mention is that the users who play Dota in China are not launching Dota via Steam, they're launching it via a separate launching application, which is not running the survey on their data. So the data that you're looking at in the hardware survey currently, which I'm sure a lot of you check in on that frequently, is not including those Chinese Dota players right now. So the data I'm showing you right here is kind of, it's a different and very interesting data, and they are a large player base even for a relatively recent launch in China. Now this particular data comes from a cybercafe partner of ours in China, which illustrates a whopping XP usage right there. So if you're a DX10 or 11 game, those customers can't play your game. And so even backing away from just particular cybercafes and looking at users in general who are playing Dota in China, we can see that the pie chart on the left, which is showing the OS share, still has that great big blue chunk there of 45% of folks that are running XP. We think that maybe this number might even be a lower bound, and as we reach even more and more players in China, that possibly that number goes up. I mean, obviously the cybercafe data maybe would indicate that. But the pie chart on the right is interesting. Their hardware is modern, and so I think we could go use OpenGL to access those features, assuming that we can get the driver story where we want it to be. So Source 2, you'll probably hear some folks mention that here at the show. It's what we're calling our next engine. We're not talking a lot of detail about the engine, other than to say it has multiple rendering backends. OpenGL is just one of them. The engine itself has some sort of D3D isms to it because of its heritage. So for example, we rely on separate shader objects, that is, a separate vertex, pixel, geometry shader, et cetera, rather than one big monolithic pipeline like you would see in OpenGL, unextended OpenGL. So we also translate our HLSL to GLSL. So we still have some D3D isms to work through there, but we would like to stop doing that and just write GLSL, just write to OpenGL, and maintain one 3D API, one renderer across all of our various targets. We're working closely with the hardware vendors to be able to do this. Obviously, AMD and NVIDIA and both Intels, if you weren't aware of that, they have different driver teams for Windows and for Linux, which requires, for us anyways, a little bit of juggling of evangelism between the different guys there, and obviously Apple as well. And recently unlocked this achievement in which we received 3 private driver drops in one 24-hour period. So we're working pretty hard with these guys and pretty closely. So for us, the biggest near-term challenges to achieving this pretty lofty goal, I think, of moving to OpenGL entirely, the biggest challenges are solving the problem of shipping shaders. There's sort of 2 main components to that. One is validation. Did the shader code that you wrote or translated from HLSL in our case, is it valid? Is that valid GLSL? In the past, you've had to actually all the compilers were built into the drivers, and there's some kind of nasty implications for that Dan will go into, and we're pretty happy with some solutions that have come along in that area. And also an efficient shipping representation is a big part of that. Dan's going to talk about that as well. Graphics debugging is a big challenge, and capturing repro scenarios, which is kind of related to the graphics debugging challenge. It's often a nice way to package up a bug to send off to a hardware vendor that they can work on without necessarily getting completely engrossed in your potentially to them esoteric build environment to really get involved and run your game, for example, on their side of the wire. So for the rest of the talk, Dan is going to dive into the validation work that we've been doing at Valve, and Rich and Peter are going to talk about WebGL, which is a new open source tool that Valve will be shipping later in the year that they've been developing, which is targeted at OpenGL debugging. So now I'll hand off to Dan.
All right, thanks, Jason. So I'm going to talk now about some of the work we've done in Source 2 around shipping shaders. Specifically, I'll talk about how we translate our shaders from HLSL to GLSL, how we validate that those shaders are correct using an open source tool called GLSlang, and I'll also talk about some challenges around the representation of shipping shaders, namely compile time performance of shaders, as well as shader portability. I'll start with the topic of translation. So just for review, all of Valve's titles today on Linux and Mac that run on Source 1, all of the shaders are translated from DX9 assembly into GLSL at runtime. Now, Valve has shipped a lot of titles like this and it's worked well, but it has some significant downsides. One of those is that debugging is really difficult. If you're trying to debug a shader, you basically have to have the HLSL open in one window, the DX assembly in another, and in yet another window, the GLSL translation of it, and it's just very hard to find the source of issues. There's also a loss of information. Just as an example, in DX9 ASM, we don't know whether a sampler is a shadow sampler. So in Source 1, we have all kinds of nasty hacks where we look at the name of a sampler to determine whether it's meant to be a shadow sampler. And there's other issues like that that were just very difficult to work around. Finally, it's not extensible at all. As new OpenGL features came online and shading language features that we wanted to use, we had absolutely no path to get to them because all of our shaders were transformed first into DX9 assembly, and that's done via the D3D. So for the new engine Source 2, it was decided early on that we wanted to solve some of these problems by translating from HLSL to GLSL at the source level. It would be a lot easier to debug. As new GLSL features came online, we'd have a direct path to enabling them. I should say we did look pretty seriously at translating from D3D 10 and 11 bytecode, and in addition to all of the issues I mentioned with DX9 assembler, another issue with D3D 10 and 11 bytecode is that it's not as well documented and it's not as locked down. So we're really very hesitant to go down that route again. So at the beginning of the project, we wanted to see if there were any options out there that would solve this translation for us of HLSL to GLSL, and we evaluated the tools that were available. We took a look at HLSL to GLSL fork. This is a fork on GitHub by Unity of a project I actually worked on some years ago at ATI. And basically it has a HLSL grammar that's parsed using Lex and Yak. And from it, it generates an abstract syntax tree, and then in the back end, it produces GLSL. Unity, I believe, uses this project for translating shaders on OpenGL ES and potentially some other platforms, I'm not sure. But it's not compatible with DX10 and 11, and in their own release notes, they've said that they don't intend to modify it any further to support shader model 4 and 5. And for us, it looked like it was going to be a lot of work to go in and modify this tool. Ryan, who just spoke in the last session, has developed a tool called Mojo Shader, and there's another great open source tool, but also it's only a shader model 3 at the moment. As I mentioned, we were not interested in doing DX10 and 11 assembly, but I did want to mention a couple projects that are out there in case you want to go that route. One is the HLSL cross compiler, and this was developed by James Jones at Imagination Technologies. It's up on GitHub, and it'll basically crack the D3D 10 and 11 blob, a Freudian slip there, and from it it'll generate GLSL. Rich, who will be speaking next, also has a project up on Google Code called FXDIS D3D1X, and that'll take a D3D 10 or 11 blob and convert it into an assembly-like representation. So if you wanted to go that route, there are some projects out there, but as I mentioned, that wasn't a solution for us, and none of these looked like they were really going to work. So what we decided to do is that we realized we already actually have some infrastructure in place for parsing HLSL. We have an ANTLR-based grammar. ANTLR is a parser generator tool. And we already parse some of our HLSL on the D3D side. And the reason that we do this is that our engine needs to know about semantics and some other information that's embedded inside of the HLSL. The grammar that we have is not a full HLSL grammar by any means. It basically just blindly accepts all of the code, say, inside of a function body. But it does understand the pieces that we need to translate to GLSL. So what we decided was we'd use this as a basis for building our own translator. And the basic approach that we took is, first of all, we wanted this translator to be as absolutely simple as possible. So wherever we could differentiate between the two languages using macros, we did that. And I'll talk about that a little bit more. We also basically were not interested in solving the problem that some of these other tools do, which is translating the entirety of HLSL to GLSL. We were only interested in being able to translate our shaders. So we decided to institute a coding standard for our shaders that's also checked at compile time, where we would write GLSL-Compatible HLSL, and I'll talk some more about that as well. So basically what we did is we extended this ANTLR-based parser. We stripped out these HLSL-specific constructs that we were already looking at on the D3D side. From them, we would interpret them into GLSL-specific constructs, generate a GLSL main around our HLSL main function body, and that would serve as the main basis of translation. Another goal we had with the translator was that we wouldn't have to do reflection at runtime. By that I mean we didn't want to have to query for locations of uniforms and which uniforms were active and have to figure that all out at runtime. We wanted to do that as a pre-process, much like we do in D3D, and I'll talk about how we did that as well. So as I mentioned, wherever we could, we differentiated between the languages using macros. So all of our vector and matrix types, we simply pound-defined away the differences between the languages. Likewise, all of our shaders are written for accessing textures and defining textures using macros that we built. And basically, this meant that we could define those macros differently for each language without the shaders having to worry about differences between accessing 2D textures and shadow maps. All of that's in macros. And then we built up a library of built-in functions, basically where we encountered HLSL built-ins that did not exist in GLSL. We just started developing a little library of them, and Saturate's a good example where you can just wrap that around a clamp. And generally speaking, that was very easy to do. So as I mentioned, this translator parses the HLSL semantics, and I wanted to show you a little bit about how that works. So here we have a vertex shader input and output structure, and what our parser would do is we look at the semantics on the input structure, and we look at the names of the variables, and basically we strip out these semantics, and from the input variables we'll generate global vertex attributes. We do the same thing for the outputs of the shader. In this case, we're looking at the output of the vertex shader, and we would know in our translator that SV position, which is a HLSL for system variable position, is going to map to GL position. So we'd ignore that for the moment and generate outputs or varyings for the normal and UVs. So basically, to review, we start out with this as HLSL, and after translation, this is what the GLSL looks like. The next thing our translator does is it automatically generates a main where we automatically declare these declarations for the input and output variables. We copy the input attributes into the vertex shader input structure. We'll call our original HLSL main, which follows a function signature where it takes the input as a parameter and returns the output. And then we copy those outputs into varyings, and in the case of the output pos, we know that that needs to go to GL position. So that's the basic idea around how we do that translation from HLSL to GLSL. HLSL also allows a lot of things that GLSL does not, and we basically came up with a coding standard to make it so that our authors who are writing shaders would write HLSL that would be compatible with GLSL. As an example, HLSL allows very loose conversions between types. Here we're implicitly converting from a float to a float 3. What we would say is don't write your code like that. Write it with explicit conversion, and then it'll be compatible with both languages. I wanted to mention that the syntax here where we're doing a scalar swizzle is part of GLSL 4.2. And in general, this shading language 420 pack extension that's part of GLSL 4.2 adds a bunch of features to the language that makes the two of them a lot closer and makes translation easier. So we enable that extension for all of our shaders. HLSL allows C-style casts, GLSL does not, so we just convert that to constructor syntax, and that works in both languages. HLSL allows you to have conditionals that are just tests on an integer, whereas GLSL requires Boolean expressions, so we just always write Boolean expressions. And HLSL allows static local variables, and GLSL does not, so we just don't use them. Now, all of these rules, as I said, are part of our coding standard, but also during validation, at compile time, we check that our code is compatible with GLSL. So it's very much an integrated part of our development now, where our developers are authoring shaders, they'll know right away whether their shader's compatible with GLSL. Some other things we do is that we use the STD140 layout qualifier on uniform buffers. And this basically defines a set of rules around how types are packed into uniform buffers. And what we do on the HLSL side is we actually generate pack offset qualifiers on the constant buffers that exactly match the STD140 rules. And what this means is that our layout in memory for uniform or constant buffers in the D3D parlance are identical. And our engine doesn't need to care about whether it's running on D3D or GL. The in-memory layout of constant buffers is always the same. As Jason mentioned, we use separate shader objects, which allows us to compile and link each shader stage independently, much like D3D does. And we use this shading language 420 pack extension. The final thing I wanted to talk about with translation is the shader reparser. So as I mentioned, we had this goal that we wanted to avoid doing any runtime reflection. We didn't want to worry about the fact that when you compile and link a shader, each implementation of OpenGL will assign uniforms and uniform buffers to its own implementation dependent locations. We wanted our shaders to be able to be baked in as a preprocess and not have to do this at runtime. And this is the same thing we do at D3D. So the way we do this is that after we've done our translation and have the original GLSL, we validate it to make sure it's syntactically correct. And then we perform reflection on the shader where we query for all of the active uniform buffers and samplers. And then what we do is we go through and we insert binding qualifiers on our uniform buffers. So this will basically say that this per view constant buffer is bound to a particular uniform buffer binding. And we do the similar thing with samplers, where for all of our active samplers, we'll insert a binding qualifier that binds it at compile time to a texture unit. After we've done this reparsing, we validate it again, and then we have our final GLSL. So the key point here is that by inserting these binding qualifiers, we are able to avoid doing any reflection at runtime, and our preprocess tool knows the location of samplers, what texture unit they're going to be bound to, and what uniform buffer location the uniform buffers will be on. So I've talked so far about how we translate from HLSL to GLSL. I want to talk now about how we validate that our GLSL is correct. So the problem is, if you're writing GLSL, for those of you who have, you know that each OpenGL driver has its own compiler. And this can mean you can run into bugs where your shader works on one driver but not on another. In D3D, you don't have this problem because you can use FXC or D3DX to find out offline whether your shader is correct. So basically, the problem is OpenGL compilation is tied to what hardware you have and what driver you have. We wanted to be able to know whether our shader conformed to the OpenGL specification across all implementations. So one idea we had was, hey, maybe we could just compile our shaders on every driver that's available. And we actually went down the route of exploring this, where we have a distributed compilation tool, and we modified it so that it could go out on our network and find, say, all the machines that have a particular NVIDIA GPU with a particular driver or AMD GPU with a particular driver. But this was just incredibly painful. For one thing, our distributed tool that does this uses our own internal development machines, and keeping everyone up to date with drivers was just a nightmare. And also, hitting all hardware combinations just was too painful. We thought about using CGC, which is NVIDIA's tool that can take GLSL or CG as input, and well, it compiles it and can produce HLSL, GLSL, or GL assembly as output. The problem we had with this tool is that, first of all, NVIDIA pretty much end-of-lifed it in April 2012. It hasn't been updated since then. Also, it really only tells you whether your shader is correct for NVIDIA because it basically contains their compiler infrastructure. We took a pretty close look at Mesa's parser, and we thought about using that, and it actually looked like a really good option, although at the time we were evaluating it, it was a little behind the shader features that we intended to use. But we were thinking about using that. However, as we thought about this problem some more, we realized that this is not just a problem for Valve, but basically anyone who's developing OpenGL using shaders. And we came to believe that the right thing is that OpenGL should have a reference implementation. You should be able to find out offline, is your shader conformant with the spec? And we went around and discussed this with other ISVs and within Khronos. And thankfully, Khronos came through and selected GLSL as a reference implementation. So I'm going to talk now about what GLSL is and how we use it. So GLSL is an open source tool. A bit of history about it is that in the early days of OpenGL 2.0, 3D Labs produced a GLSL parser based on Lex and Yak, and they open sourced it. And 3D Labs subsequently went out of business, and some of the people who were there are now at Lunargy, and they've basically rewritten this parser and extended it for modern OpenGL. It's open sourced under the modified BSD license, which is very liberal. It has a C and C++ API, so you can access it programmatically. It also has a command line tool, and it's currently available on Linux and Windows. It's pretty vanilla code, so I'm sure you could easily compile it for macOS as well if you tried. I haven't tried myself, but it should be simple. Valve actually worked very closely with Lunargy and actually funded some enhancements to GLSL to make sure it could support all of the features that we needed. Namely, support GLSL 4.2, support geometry, tessellation, shaders, the 420 pack extension that I mentioned, as well as GPU Shader 5. It basically supports all of that. There's some small corner cases where it doesn't yet, but it's very close. We also worked with Lunargy to develop a reflection API. As I mentioned earlier, the idea was we wanted, as a pre-process, to be able to find out what the active uniforms and uniform buffers were in our shaders. So we worked with them to develop an API that's implemented in GLSL, so you can find out that information about your shaders. So the way we use GLSL in Source 2 is that basically every shader we have is validated and reflected using the tool. Our distributed compilation system will, farm out compilations to multiple machines, and each of them invoke the compilation using GLSL. And because there's no hardware dependence with GLSL, it doesn't matter what hardware is in the machine. This tool has been hugely valuable to us. First of all, it's helped us find a lot of cases where each of the three vendors were accepting invalid GLSL. It also led us to find cases where they were not accepting correct GLSL, and that led us to file bugs against IHVs, which they've fixed. So, it is possible that GLSL could have a bug, but it's tested a lot, and more so as time goes on. They run the conformance shaders against it, and so far we haven't found a case where GLSL has rejected our shader and turned out that it was correct. So it's a very valuable tool. I'd encourage you to check it out. This is actually pretty breaking news. I think Khronos should by now on the website or later today announce that GLSL has been selected as the reference implementation. This is the link to the landing page for it, which has a link to where you can get the source code as well as download the binaries. It should hopefully be on khronos.org later today. I think I looked about an hour ago. It wasn't there yet. But I'd encourage you to check out this tool and potentially integrate it into your pipeline if it's as useful to you as it is to us. So the final topic I wanted to talk about was some challenges around the shipping representation of shaders, and namely, I'm talking about challenges with shader compile performance as well as portability. So for review, in OpenGL today, you basically have two choices around how you ship shaders. You can either ship source, or you can use program binaries. Program binaries basically allow you at runtime, after compiling and linking a shader, to query the driver for a binary back that you can use on subsequent loads. And the program binary is basically an opaque hardware-specific format that should give you much faster compile times because it's already been compiled by the driver. So one issue we've run into with using source is that compile times are a lot slower than using D3D bytecode. This has been particularly an issue for us in Source 2, where our shaders are much longer because we are translating directly at the high level, whereas in Source 1, our shaders had already gone through FXC and been optimized down to assembly. I should mention that on drivers that have a shader cache, for example on NVIDIA, subsequent compiles of your shader are plenty fast and just as fast as D3D because they basically hash your shader source, and the next time around we'll use a cached copy of it. But the first time you compile your shader, it will be a lot slower than using D3D bytecode, and that's an issue, say, on the first time you load your level or the first time you run your game. Another issue is IP leakage. In other words, that any debugging tool can inject into your application and get access to your high-level source. This may or may not be an issue for you. Some people don't care if anyone can look at their shaders, but for some developers, that's something they don't want. Program binaries solve some of these issues, but they create issues of their own. The biggest issue with program binaries is that they're extremely fragile. Essentially, the program binaries are tied to the driver and the hardware, and the driver's free to fail to link your program binary successfully for any number of reasons. And basically, we've found anytime you update your driver, and for sure if you update your hardware, you need to regenerate your program binaries. And what that means is your GLSL still has to be available, because the way you generate a program binary is by using the API and using source first. So we wanted to look at what could we do about this shader compilation performance and quantify how bad is it really. So what we did is we ran an experiment where we took our most complicated pixel shader in Source 2, and we tried compiling and linking it on 2 different drivers. You can see one, it was around 700 milliseconds, and on another it was around 200. And then we turned on the shader cache in driver A and compiled that shader again. And basically you can see there's this huge gap in performance between compiling from source or using the shader cache. We wanted to see if maybe we could improve this performance by optimizing our GLSL. So we did another experiment where we took this same shader and we ran it through NVIDIA's CGC tool, which basically produces assembly-like optimized GLSL. And you can see that, yeah, you do get a lot better performance. 700 milliseconds goes down to around 100, but still the shader compilation performance is nowhere near program binaries or shader cache. So where this has led us is to believe that the right thing for OpenGL is that it really needs to have an intermediate representation, or IR, for shaders. This would solve a lot of the problems we're seeing at once. It would give us faster compile times that should be around comparable to D3D-IL. If IP leakage was a concern for your shader, you wouldn't have that problem anymore, because you'd just be giving IR to the driver. It also would allow you to have a full reference compiler stack that was completely offline and could be done as a preprocess. You can imagine GL-Slang having a backend that can produce IR, and then you could just do your compilation once, and that should also help with a lot of these shader portability challenges, because hopefully you'll have a lot less bugs in the drivers with compiling IR. Now, for all of these reasons that I've mentioned and some other ones, this has already been tackled inside of the OpenCL working group in Khronos. They have a spec called SPIR, or Standard Portable Intermediate Representation, which is derived from LLVM-IR, and basically it allows you to compile your OpenCL C kernels into IR, and then you use that at runtime. And Valve is just beginning the process of advocating for an IR within Khronos. We think this is the right direction for OpenGL. We've talked to a lot of other ISVs and IHVs who seem to agree with us so far. It's very early days yet, but we just wanted to give you a glance at sort of future direction, that where we hope to move things is to get to an IR so that shipping OpenGL shaders becomes a lot easier. So to summarize, I've talked to you about how we translate our shaders from HLSL to GLSL in Source 2. I've talked about how we validate those shaders using GL-Slang, an open source tool. And I've talked about some of the challenges around the shipping representation of shaders in OpenGL. And with that said, I'm going to turn things over to Rich, who's going to talk about a debugging tool for OpenGL.
So hi, my name is Rich Geldreich. I'm a graphics programmer on the SteamOS team. And we've got about 40 minutes of content that we've squeezed down to around 20 minutes and a demo, so I might go a little fast here. So I've done a lot of GL and D3D debugging over the last few years. It's pretty much been my life. And over the last 2 years, I've done a lot of GL debugging on Windows and Linux when I can. And one of the big problems is the story for GL hasn't been very good. I think Ryan pretty much said it very succinctly. So we think we can do something that a lot of developers will find useful, and we realize that Well, actually, if we can create an interesting set of tools that maybe some vendors would find it useful too, and maybe we can actually ship it in Steam as well. So I want to introduce what we're working on. It's called Voggle. It rhymes with boggle. We're going to open source this. We think a community developers can do a better job than 4 or 5 developers at Valve and RAD Game Tools. We think integrating this product or this set of tools into Steam, there's actually a lot of value in that. How many times have you received bug reports, either game rendering problems or driver rendering problems from people, customers that are playing your game, and you can't reproduce the problems? Well, we think shipping our tracer and our replayer, whatever, to customers and then letting them upload traces to the Steam cloud actually would be an interesting thing to do. So we're committing ourselves to that. We're making a vendor-neutral debugger. So if I had a nickel every time I ran some vendor's debugger, and I'm not bashing anybody's debugger, I love them all. But if I had a nickel every time I tried to trace one of our apps on vendor X's debugger, and I tried to replay that trace or debug it and it crashed, or I tried to take vendor X's debugger and use it on part Y, and I have a problem, I go to the vendor and I ask them to fix it. Well, if I had a nickel for every time that happened, I would be a very wealthy man right now. So I want to try to fix that. No special app builds are needed. So we test Steam apps right now, and our goal is to make sure our debugger is compatible with all of the Steam Linux GL apps and SteamOS apps too. So we're committing ourselves to 4 features. We have 3 listed on the slides here. 4 major features. There's frame capturing, which you're probably very familiar with if you ever use another tool like Pix for Xbox or Pix for Windows or whatnot. Full stream tracing, which might be new to a lot of developers, which is where we capture every GL call and put it into a file. And we're committing to supporting real-time full stream tracing and replaying. Trace trimming. So that's where you take a really large trace and you make another trace, which is a subset of that. We're optimizing our replayer a lot. So we have telemetry integration, like we've done with our previous Source Engine games. And we are tuning our replayer class so much that we are committing ourselves to being able to replay most game workloads faster than you're able to pump out GL commands. OpenGL usage validation. So if you ever use a D3D debug runtime, you're probably familiar with what value that adds to your experience while you're developing. Well, we want to do the same thing for GL too. We want to make sure that your experience is the same across all the drivers. So if you do something like call GL without an active context, most drivers, if not all of them that I'm aware of, won't give you a warning or error about that. So regression testing and benchmarking. These are things that we need to make this debugger work. So while we're modifying the debugger source code, it's impossible at this point. It's gotten so complex that we don't have an accurate mental model of how those modifications will impact the hundreds of games out there. So we're just creating a big automated regression test. So that also goes to the next point, which is robust API support. So we're committing ourselves to the things you would expect, GL3 and 4, but we're also committing ourselves to compatibility context as well. So if you use, we're not recommending that you use these things, but if you use client-side arrays or display lists, begin and end, we support that stuff. And of course, we're creating a UI. So our goal is you be able to control all the features from the UI. And it's not just a debugger or state visualizer, it's also just an editor. So real fast, some of the key concepts, and I've kind of already talked a little bit about this. We support JSON traces. We have very strong support for that because that's how actually we are developing and debugging our debugger. So you can take a binary trace, which is just a bunch of variable-sized packets in a zip archive at the end. It's actually just a valid zip archive. You can take a binary trace and you can losslessly transform it to a JSON trace and back, and we guarantee the lossless nature of that transformation because we actually serialize and immediately deserialize the key things like floats and doubles and make sure they can go to text right. If not, we just store them as hex. The archive at the end, or as a loose file if it's a JSON trace, contains things like a state snapshot, which is just more binary or textual JSON, a frame directory, backtrace maps, basically any data that we need to play back that trace. And you can unzip the trace archive and then delete the trace archive and still play back the actual trace. So a state snapshot is actually the big value add here versus some other tools that we've seen. So state snapshot is basically kind of what you would expect, except we guarantee that it's restorable, and we test that because our entire tool set depends on this. So we can take all the GL context, and we can put it in a big object, and we can serialize that as binary or textual JSON. Our textual format is sorted in a way that you can easily diff it with any to-diff tool like Beyond Compare, and that's actually something we want to make better in our UI, to be able to diff state snapshots between 2 different draws or frames. Full stream trace, pretty much already described that. It's basically all GL calls stored into the trace file with optional state snapshots, either generated at trace time or generated with an offline tool. And those are basically, like if you're familiar with video coding, keyframes. So we can quickly seek, and I'm going to show you that in a demo in a second. Between, if you have a 60 gigabyte capture, like 10 or 20 minutes of a game, with other tools, you might have to play back from the beginning all the way to the frame of interest before you can do anything. And we want to fix that because we know that's a pain point. We felt it ourselves. So a single multi-frame trace is basically either a trimmed trace, a trace that you've taken and extracted one frame from, or a subset of frames from, or while tracing your game, you've clicked the button in the UI and you've just captured one frame, and you can capture more than one frame too, and you can keep on doing that too. While you're still in that same process. And so trimming is pretty easy for us. We can take state snapshots either during trace time or replay time. The actual state snapshot code doesn't have any knowledge of where it's being executed. It's just GL. We do GL gets for 99%, if not 99.9% of the state that we get. We shadow very, very little. I'm very aware that I've used other debuggers that try to do shadowing, and invariably they somehow diverge from the state that GL has. So with that, I want to get to the demos. So I'm going to, if you can switch over to the other machine. There you go. So this is KDE, and this is all I use personally. I've banned Windows from my life for the last year. I'm completely on board with this. I find myself more productive under Linux than I've ever been under Windows in the last few years. When I go back to Windows now, and I'm going to bash Windows, I feel like I'm back in 1995, honestly. This is an operating system made by programmers for programmers, so how could you not want to explore this space? So what we have here are 3 replayer processes going right now. This is just a little 4-core machine with a 780 Ti. I was going to show you this little demo on a 680, but we burned it out. So within 5 minutes, the machine got so hot that display started to get corrupt, and NVIDIA's driver did a pretty amazing job of trying to keep going. We were really impressed that even though something failed in the hardware or cooling or whatever, it just kept on going. So we realized we can't show that. So this is on a 780, and it's been running this entire presentation, and it hasn't crashed. We actually let this run for 4 or 5 days. So we're running this on Steam boxes too. We want to make sure that the cooling is adequate, and this is a very heavy workload, and these are all GL calls. So this is not a video. And this is the replayer live right now in what we call benchmark mode. So I'm going to get rid of those, and these are all full stream traces. And what I'm going to do is I'm going to load up a Metro Last Light trace, and this is about a 60 gigabyte trace that I did a few days ago. I was talking to Peter. I was a little distracted. And then I generated state snapshots every 100 frames. I probably went a little overkill on this. And what I want to show you here real fast is this was actually started as an experiment. We didn't know how well this would work. At first, it was horrifying to me. You think, wow, we're going to blow away all the context, and then we're going to recreate all the state, link all the programs, and then continue playing back. That's going to take 30 seconds, a minute. I mean, my experience with games is they're really slow to load, and kind of embarrassing for game engines. Not really. Let me show you this. So this is a full stream trace. We've played back from the beginning, and I'm going to pause it right here. So we just taken a state snapshot of all the state up to here, and you could trace later on in the game, and it's pretty much just as fast. This is on NVIDIA right now, but we've tested this a lot on AMD, and we've just started the test on Intel as well. And it works great on all of these drivers. So right now, what it's doing, it's pumping this frame. So it's taken a state snapshot earlier, and it's just pumping the same frame out over and over again. It's recreating all the context. This is actually really robust with all the drivers, amazingly, to me, from my D3D experience. Usually I think, wow, creating a context is a really traumatic thing. And the drivers, or at least NVIDIA's driver, caches the linked programs, so that's actually really fast. What I'm going to do now is I'm going to seek to the 90% point in this large trace. And what it's going to do, it's going to deserialize a state snapshot. It's going to bring it in memory. It's going to blow away all the context. It's going to recreate it, and then continue playing back. And so while we're playing back, we also remap across the trace domain, handle domain, and location domains, and the GL domain, because as Dan said earlier, things like when you link a program, if you haven't actually done anything special, the locations can change. And of course, handles can be different amongst drivers. And so we remap on that. So this trace plays back on AMD. We've tested that, and we're trying to commit to, as long as the game doesn't use any weird, funky extensions, that it'll play back on all the drivers. And we also have a compatibility mode trace option where we'll attempt to put the app into a mode where it doesn't use extensions. Like in this case here, the game isn't actually using program binaries. We turn that off, and it's actually just always using a GLSL. So another thing we can do real fast is, so let's say we find a frame of interest, and I'm playing back in slow motion here. Let's say we just find a frame of interest, whatever, and we're going to add a UI to all of this. This is just a simple test UI. And so right now what it's doing is it's taking that state snapshot that it just made of this frame, and it's basically putting it into a new trace. And now it's loading that up, and it's doing that right now. So while that's happening, this trace will keep on playing, so I'll pause that. So now it's loading that up, and you'll be able to see in a second, you're going to see the frame that you saw earlier. So this trace was written into a separate directory, and it's now this completely separate standalone thing, and that's coming up. So there it is right there. So, and it's actually pumping that frame right now. And so while it's pumping that frame, you can change the JSON, you can change the shaders, and actually see that. And over here, we've got the JSON actually for that particular frame. So we don't have many minutes left, so I'm going to pass it on to Peter.
Okay, so as Rich mentioned, we're putting a user interface to this tool here, this replayer. So we've got the Vogel editor, and well, right now I've just loaded up a trace that we took, I don't know, 2 weeks ago, a week ago, and you don't actually know what that frame is. So I'm going to use his same replayer class and just play the trace. You can see that we're just about quitting out of Left 4 Dead 2 here. And so that's the one frame that we're looking at here. And across the top of our UI right now, so right now this UI's had maybe 6 weeks worth of work, not very much. There's a lot of things we want to do with it. We have this CPU-based timeline, and we color the most expensive call in red, so you can very easily see that that's the most expensive call. And we have all of our API calls down the left side, everything that was made in this particular frame. And as I go down, let's see, I went way too far. So you can go down. As I kind of cursor up and try to find this expensive draw call, you'll see that at the bottom of the window, we have the entire call stack for every API call that you've made. So as you're trying to figure out what made this exact draw happen, you can look back in your call stack there and find out what's going on. Where is it? There we go. So we have this GLText subimage 2D. It's taking like 100 times longer than some of the other calls. And you saw the flicker there. We were actually running the replayer, getting a snapshot at that exact API call. And so over here we have that big state snapshot of all the state, all the GL state. There's really a ton of it. And we have all the, let me make this bigger, at the bottom here. We have all the textures, render buffers, frame buffers, programs that have been used in the application or been created up until this point. And by default, we grab the current state, and the texture that's being uploaded there, we can see that it's this, the video here. This is actually the video that's playing in the background of that menu. So if we had some performance problems with this app, we might decide to just kill that video or just pause it, show a still image, and we could get rid of that big red chunk in the middle of the frame. Something else that we're doing that not many other tools do is we have some machine info here. So we're capturing all the modules that have been loaded up into the application and their address space. We show out the environment list, all the environment variables, some command line options, information about the machine itself, clock and driver information. And one thing, like I said, we've only put about 6 weeks of work into this. So we really see this as an editor. As Rich said, we're dumping all this out to JSON. So we can, the plan is to just be able to diff this state right in the window, type right back into it, change things. We should be able to delete draw calls, add them back in, change API calls without much work. So that's kind of the direction that the tool is going. And I guess with that, I'll pass it back to Rich.
Cool, if you could switch back to the slides. Cool, okay. Here's our current app compatibility. So I'm a very strong believer in testing our debugger in actual applications. So we have a lot of artificial samples. Luckily, in the GL world, the GL community has done a great job creating tons of samples and tests. So we're good there, but at the end of the day, we want to be compatible with games. And so we probably have more games than what we're listing up here. It's just we can only test them so quickly. We just got shareless support or multi-threading support, for example. So Metro is one of those games. So anyway, we have all the Valve games as well. We think that the Super Bible samples are really, and other samples from books and stuff are really good to support because that's probably most programmers new to GL are going to go to. So I wanted to make sure when you left the session, you'd have something to take back other than we're making a debugger. And so here's what we've learned while going through your applications, trying to make sure our debugger can play them back right. Incomplete textures are shockingly common, and this is a pain point for us because we have to capture something that we'd rather, and I think the vendors too, would rather not see you doing. So an incomplete texture is basically when you only fill in part of the mipmap chain for a texture, but you don't set the text param called GL texture max level. And if you're using GL4 with GL text storage APIs, you won't run into this. But if you're using older stuff, that can be a problem. We capture that and we play that back, but we give you a warning about it. Calling GL with an active context can be really bad, and it can be super bad if you leak. And if you leak over time, you crash. So we do our best to warn you and give you errors about things like that. I've seen other things like bogus handles. FBO completeness is kind of annoying. So the problem with that is you can test on one driver and think that your frame buffer objects are complete, but in reality, you should test on all the drivers because some drivers validate more than others. Shipping with GL errors, I think this is really, really bad, and because when there's a GL error during replaying, I have to track down is it my problem or is it the application's problem. It turns out many apps just ship with GL errors. Sometimes I think personally you should call GL error a lot, at least during development. And I know there's also an ARB debug output. You can use that too. Debug context warnings. So I see a lot of debug context warnings, even the biggest games. And then getting to perf, some of the biggest games, I look at their histograms of the top 10 calls that they make and the frequencies, the number of times that they're called. And there's really trivial DSA. That's an extension that allows you to distill down one or two or whatever GL calls into one. There's really trivial extensions that you can use on most drivers to get perf back up, especially relative to D3D. So you should probably use that. A redundant state setting, you probably heard this over and over and over again. You should check for that, and we do have a feature that lets you get a measurement of how much redundant state is set. And finally, there are some concepts from D3D that are different from GL. Linking programs is one of them, and I've been surprised many times by some subtleties related to this. So just study that very carefully. And real fast, what we're going to ship soon is a tracer. And that's actually loadable. It looks like just like libgl, and it's either loadable by Steam or you can manually load it. It's compatible with SDL. It just works there if you use SDL, and I'd recommend you do. We have a replay tool, and it's kind of just a junk drawer. I don't want to use the word junk, but it's basically just a tool that can let you do all kinds of stuff with traces, including finding. So I find that I use grep a lot on JSON, but at the end of the day, sometimes you want to narrow down by regex or whatever. And we're going to commit to shipping an editor too. And we're making a benchmarking tool, which will be a separate replayer that's optimized purely for performance. So ultimately, we have one replayer now, which has a benchmark mode. We're splitting that into one that's for debugging and one that's for performance analysis. So our goal is we want to be able to replay your streams faster than you can create them in your application, which we think is totally achievable. And we're also client server, and we're already testing on Steam boxes right now. So you can we're going to show this in the breakaway. You can trace on a Steam box and then play it back either on the Steam box or in your local system. We're supporting RAD Telemetry Integration too. We're actually using this, and this is actually a trace right now of the replayer tool. And RAD Telemetry is basically an intrusive profiler. You go in, you add a few lines of code to your game, and then you get a really nice visualizer. It lets you visualize where all your CPU time is going. And so one last thing is this is a JSON trace file. This is actually a valid trace, and it's really simple. This trace file is replayable by our replayer. We're going to ship a bunch of hand-authored traces. It's actually a great way to learn GL is something like this. So you can go and I don't know if you can see that really tiny font, but we create a context in this trace. We make it current. We set the viewport, all the things you normally do. And this is all valid from our replayer's perspective. A machine-generated trace has a lot more information, but most of it's optional, and it generates that triangle, and you can play this in a loop over and over again, and then sit there and hack on the JSON. It's pretty cool. So anyway, we're going to have more information in our breakout session later on. I think it's at 5 or something. I don't remember. But anyway, richg42.blogspot.com. I have the slides I couldn't fit into this presentation. So I want to thank Jason Mitchell, especially for inviting us to talk today.
All right, so I just want to send you with a couple of quick ideas here. First of all, OpenGL is a conversation. It's extensible. It's constantly moving. This does require some of your attention, however. You don't just get to wait for the twice-a-decade API handed down to you from Redmond that you don't get to actually iterate on. GL is a different beast from that. You also now have absolutely no excuses not to test on Intel. It's pretty interesting. Your customers have these GPUs. You have them too. That little blue wedge is widening over time over there. They're shipping these. From the hardware survey, you can see they're the top 3 GPUs in the list. And if you include Apple in there, those numbers actually go up. So the call to action to you is front load your move to OpenGL. This is not a port. This is your 3D API. Set up the hardware vendors to succeed. They're internally fairly biased toward D3D, as you can imagine. With numbers, we can change that orientation for hardware vendors. Manage the risk. If you have D3D and you're shipping this spring, don't throw it away. Go ahead and ship that and keep it around, of course. It's useful to have another implementation to compare against. And join the OpenGL conversation. So I'm afraid we've unfortunately run out of time in our time slot here. We need to get things switched over for Bruce, and we don't have time for questions right now. However, there is a breakout session at 5 in this room where all of the speakers that have spoken in this room this afternoon will be available. So please do come back for that to talk, because we're very interested in talking with all of you guys. Thanks a lot.